All right, morning all. It's a fair bit in this one. Anyway, welcome back to normality after last week. Clinic's still happening. Remember, today's the odd day where we go for... Oh, that's an old slide. Okay, there's the good stuff up to start with. Monday's an odd day. Remember, Monday, because we've got the lecture on now, we do the maths clinic from 1 till 2. Every other day it's 12 to 1, but on Monday we do it 1 to 2. So there's a clinic straight after this, if desired. Quiz mark redemption's still happening. Didn't get to see most people last week, so I just want to do a very quick heads up on some of the things for the mid-semester that were happening a lot. Put dollar signs on dollar answers, little stuff like that. Units in general. I might have written elephants a lot. That was just a way of saying if you said the answer was 3 what? 3 elephants, 3 grams, 3, So just to give your answer, it's units. Use brackets when subbing in negatives. There wasn't much in the test, but remember, if you're going to get minus 2 and replace x with minus 2 and it's getting squared, it's going to become positive. If you're just putting it into the calculator and you might write minus 2 squared without brackets, it'll come up negative because it's doing the squared before the minus. So just know, put brackets around any negatives if you're going to square them. Cubed and inversely were 2 words that cause issues. A lot of people maybe just skipped or didn't see the word cubed in one of the questions about, it was a ball bearing, I think. The mass was directly proportional to the diameter cubed. The word inversely, and there was some distance, Perth to Sydney or something. Inversely meant the other variable went on the bottom. So just a few key words we were missing. Positive gradients were still catching people, positive versus negative. Remember, it doesn't come from the numbers you sub in, it just comes from looking at it. That's positive. It was very similar to a revision paper, not unusual with us. It's not going to be unusual for the final exam, that the final exam is going to be very similar to the revision paper. Just if you do nothing at all, revision paper is good to do. Read, answer the question. I'm bad at this too. It's a fairly general fault. Like total amount owed to Sheldon was one of the questions. It didn't say how much interest he'll owe Leonard. It was like, Leonard would owe him. It was what's the total amount. So he had to add the initial back. There was a question that said something like we had $200. We wanted to get to a total of $240 in the account. It wasn't $240 interest, it was only $40. Just slow down and check. What's the question really going on about? The thing between, forget who I used, Jeffrey and Flynn in their bike hiring business. Oh, Monday. What would be the exact difference in cost? A lot of people did the numbers right, worked them out, but just didn't state the exact difference in costs or who was the cheaper option. So you might have done all the hard yards. Just make sure you answer the actual question. There's another one. During the first question, didn't ask what height it was after 1 second, what height did it travel during the first second. So the difference between where it was at t equals 0 and where it was at t equals 1. Remember, the order doesn't matter. If you're looking for that ABC, subbing into your quadratic equation, axis of symmetry formula, it doesn't matter if it's written backwards or not. The A is with the x squared, okay? We had one in the exam that was like this, and people just went, that's A, that's B, that's C. But A is always with the x squared, B is with the x. C is the standalone number. Vertex is a point, so if you ask for the vertex, it's not just x equals, or it's not just the y value. It's something, comma something. So vertex is a point. And just remember, any of that logarithmic scale stuff, all we're doing is Richter scale. Whatever the difference is between the Richter scales, the difference in magnitude is 10 to that gap. So like when we're talking about a Richter scale of 3 versus 5, the difference between 3 and 5 is 2. The answer was 10 squared. If it was between 5 and 5.5, the gap was a half, so the difference was 10 to the half. That's the whole thing of the logarithmic scale. So with the mid-sem exam, the answers are up. Check through it and consider that to be a third of your study for the final exam. If you can nail the mid-semester exam, a third of the final paper that repeats that material is going to be quite easy for you, okay? So the mid-sem's useful for final study for 1/3. Obviously 2/3 is all the B lectures. What else? This is something I brought up last week, but it was a weird week last week. That's just something to show a lot of people are very happy, a lot of people are unhappy with their mid-semester marks. We had a 25% fail rate, which is not that unusual for previous years. This is just looking at last year. Anyone that last year got the same mark in the mid-semester and in the final would be sitting on that line if they got exactly the same mark. You can see a lot of them are actually on this side of it, which is a good thing for us. 2/3, 66% of students last year improved their mark between the mid-sem and the final, probably also by getting on top of the mid-sem and getting it right in the final. And this little zone here is if anyone's thinking, damn, I failed the mid-semester, well, everyone in this square failed the mid-semester last year, but then passed the final exam. Like, say, this point here is from someone that got, what's that, about 28% in the mid-sem and got 75 in the final. This person got 35 in the mid-sem, 65-ish in the final. So just saying, don't give up. If people didn't like your mid-sem, just work out what went wrong. Did you not know the stuff? Had you not seen the lectures? Did it just make no sense? I suck. Whatever factor you found, did your resource sheet suck? Just work out what it was. So don't ignore the mid-sem. I know we don't do redemptions on it. We'd like to, but it's not. We're not allowed to at the moment. It's not going to happen this year. But yeah, please just have a look at, work out why things may not have been as you wanted, or they were, and repeat it for the final if things went well. The last thing there, probably after giving that speech, student feedback on teaching. Again, I know we bombard you with surveys. You may get this from, this is one we, as a teacher, choose to put out. Okay, everyone can elect to. So this isn't about the course, this is about me doing good or bad things in the course. It's a thing we put on our CV. So that should have been emailed out today. If anyone can fill that in, that'd be awesome. Even if you've got negatives to say, that's life. Be very interested. It's only 7 multiple choice questions and an optional written comment, which in the past has been things like love cahoots, hate cahoots, get a haircut, various things. That's all your decision, okay? Your names are removed. So I'll admit sometimes I can go through the comments and work out who said what. There's certain things that people say. If there's no, don't go there. Okay, but anyway, if you can fill in the survey, that'd be awesome. So this lecture, yes, it is fairly full, but it's hopefully it flows well. As in, hopefully, I just want to make total sense of all this stuff. There's some new concepts, some new terminology. Fine, let's get into it. The ogive is the first thing that probably looks like a bit off-putting, but all it is firstly we just say, what did we do last week? Last week we did, the only graph we formed last week was a frequency histogram and polygon. The histogram was the column things, historical columns, and the polygon was joining the dots basically. So this is just a review of last week, this slide, and the next one saying we maybe had a survey of 30 students asked how many times a week they had fast food. Okay, and then to plot that, we straddled the 1, put a column there, where 1's right in the middle with a height of 4, then a height of 9, and 6, and 7, and 3, and a 1. That was our frequency histogram, which often we're asked to do a frequency histogram and polygon just on the same graph. So just make sure you note it, put an arrow to it, something. That's my histogram. And the polygon was done just by joining the dots in the centre initially, joining all the dots. And the other thing we did was take it down to the axes at the beginning, one section before the first result, and take it down at the end. So that was last week's, and there's only one type of graphing we're doing this week, and that's a similar thing but cumulative frequency. Okay? So we might last week have done the frequency, this week we're looking at the cumulative frequency column. Now I've already in the tutor and the lecture done a cumulative frequency column. It was used to find the median. We're going to use it for more this week, okay, than just finding the median result. But it was a zigzag thing. It was how many frequencies, how many scores have we got so far. The first number is always the same as the first frequency. I've got 4 scores so far. And then 9 more makes 13, and 6 more makes 19, and 7 more makes 26, 3 more makes a 29, and 1 more makes a 30. And that always happened. The CF, the last CF result, is always the same as the total because it should refer to the 30th data point. So the graph I'm referring to is just plotting that column, not plotting the F column. The F column could be all sorts of up and downs, where the CF, well, it might go flat a bit, but it's not going down again. The CF column never goes down. You never subtract numbers off it. It's going to be something that's more like going uphill. So again, I'm not plotting the F column, I'm plotting the CF column. As for the histogram, I'll do exactly the same thing as last week. Let's get this 1, and I'm going to go either side of it. I'm going to make it up to a height of the CF column, 4. So my first column will just be that there. And then I'll do the same thing, but again, I'm not doing the F column, I'm doing the CF column, do it up to a height of 13. So we're going up to here, and then up to 19. You see how it's never going to go back down again. If I ever get a 0, I might go flat, but I'm not going down. And then a 26, and then a 29, and then a 30. That's my cumulative frequency histogram, the columns. Okay? Now, the ogive is basically, it's annoying that they give it a special term, but you can think of it as exactly the same as a cumulative frequency polygon. Okay? But I use the terminology they use in stats, and they call it an ogive. Fine. Polygon. Yes, it's going to be one of those days. Okay. Not today, though. Now, we don't just join the dots here, like we did in the last one. The last one I would have gone, okay, join all the dots and then come back. In a cumulative frequency polygon or an ogive, we start at the bottom corner, we end at the top corner. We keep doing these diagonal things, there to there to there to there. Now, I know I haven't explained why yet, that's coming. I'm just saying, look, this is what we do. Okay? Why? In a sec. But that's it. That cumulative frequency histogram, draw the column same as last week, just use the CF column, not the F. And the ogive is joined from the very bottom left corner to the very top right corner. Okay. Also for grouped data. We really don't spend a lot of time on this, but group data hopefully will be clear that sometimes it might say from 20 to less than 40. So for weekly students' incomes, if you just get between $20 and $40, we'll just say 7 people scored that. Okay? There might have been all different answers in there, but we just said, look, 7 people fell in that region. And from 20 to 40, well, hopefully makes sense. And I'm not going to straddle 20 and 40. I'm just going to go from 20 to 40. And I'm going to give it a height of 7. So the only difference between group data and the initial data, if you've got a data point, you straddle it. In this one, you just go from the bottom of the range to the top of the range. From 20 to 40 has that height. I know these boxes are shaded in from the computer. We don't shade them in, we just draw boxes. From 40 to 60 had a height of 17. Again, I'm doing a CF graph. I use the F to make the CF, but I'm doing a cumulative frequency graph. Then to 30, then to 36, 41, 42, 43, 45. There's my cumulative frequency histogram. And then to do the ogive, I just connect corners from the very bottom left to the top right. So cumulative frequency histogram and ogive. Now, they're their classes. They were different classes. This is where I just want to say, why draw it this way? Why are we drawing the line from the bottom corner to the top corner? This is why. It's just some random example I picked here. To create an even distribution within classes. Now, the truth is, here between 3 and 7, there were 4 results that fell between 40 and 60. The truth is, we don't know what the 4 results were. Maybe they were all 50s. Maybe they were 41s and 59s. I don't know. So there's a little bit of inaccuracy here. But we just assume when we're analysing it, we pretend that they were evenly distributed. There were 4 results in there. We pretend they were nice and evenly spread. Okay? Like this. We can use this ogive to say, well, what was the third score? The third score was a 40. Okay? So the third score is 40. We can go to this 7 and say, well, what's the 7th score? We go to the ogive and come down. We say, well, the 7th score is 60. True, it may not be exactly right, because we don't know how they were distributed, but this is our assumption. And then halfway between them, well, that must be the 5th score is about 50. So we assume the 4th score is at about 45, and the 6th score is at about 55. So that's all it's doing, okay? We're going to at one stage say, well, you know, what's the middle score? We're going to go and say, well, hit the ogive, go down and say, it was about this. We can't promise you, but it was about this. So that even distribution is why we draw it that way. But it's a good resource sheet thing. Whenever I'm doing the ogive, yeah, I join the corners. So here's an exactly typical sort of question for us. I've been given the x column and the f column. It's asked me to plot CF versus x, so I've got to fill in my CF column. And I'll say I've got 5 scores, and then I'll just zigzag all the way down. Plus 6 scores, plus 7 scores, plus 3 scores, plus 4, plus 2, and plus 3. I might do a secondary check to see that I didn't screw up anything, because I should land with a 30 there. 5, 9, 12, 19, 25, 30. Yep, Millhouse. And then if I want to plot my CF versus F, I don't need to do this, I just like to do it. It's a very easy habit to keep grabbing the F numbers when you don't want to. So I'm just going to put the line there to stop me from doing it. The first score of 1 has a CF of 5. So it's not a class like from 1 to 2, it's just 1. So I'll just go to a height of 5 for a score of 1, and then to a height of 11 for a score of 2, and then a height of 18, height of 21, 25, 27, and 30. So I'll state that was my histogram in red, and now if I change to blue pen, I'll do the ogive in blue pen, and the ogive is just connecting the corners. Straight isn't not too bad. So you can see rulers in the final exam, not essential, can be freehand. That's exactly how to be presented, but it's handy, okay? So, there's a cumulative frequency histogram and ogive. We'll get to the point soon where we ask questions about it, but at the moment I'll just make up a random question. What was the 20th score? And I'd say, well, the 20th score, I'd go to where I hit the ogive, and I'd say the 20th score was around here, 4 point something, okay? If they were exact numbers, I'm saying the 20th score is about a 4. Okay, we'll get to those questions. Another one to make is just group data. All right, if I'm doing group data, from 0 to 1 is 3. That's even easier. I've just got to go from 0 to 1 and put a height of 3. Thank you. Fine, I'm leaving it there. 5 from 1 to 2. Damn it. Who's going to stop me? Anyone? Anyone? What was I doing wrong? Plotting the F. Yep. I'm meant to be plotting the CF. So already take the 3 across, plus the 5, plus the 3, plus the 4, plus the 2, plus the 0, so it's going to go flat a bit, plus the 3. Check that they do add to 20. We've got 5, 9, 12, and 8. Yep. And to stop me doing that again, I'll put my line there. So 0 to less than 1 was 3, so from 0 to 1 was a 3. And then to an 8. Why does it do that? And then to an 11. And then to a 15. To a 17. There. And it stays at 17. And it goes to a 20. All right. So my histogram is done there, and my ogive is stays flat. Okay, so that's the extent of what we get asked to produce graphically. Last week's frequency ones and this week's cumulative frequency ones. So now let's go into why. What will we use it for? And other times we'll just get given one that's already done. Why will we use it? Okay, quartiles. If you look at that string of data, all of that data, it's been split into 4 bits. And the things that cut into 4 bits are just quartiles. Q1, Q2, Q3. Technically you could say there's a Q0 to the left and a Q4 to the right. It's not really of interest. But that's the first quarter of data. And then the second quarter, third quarter. So the Q2 is really just called the median, because the Q2 is exactly halfway. What's the 2/4 mark? 1/2. The Q1 you'll also find, I'll call it Q1, but textbooks will call it the lower quartile of data. Q3 will get referred to as the upper quartile of data, okay? Just the top and low quarter of data. And this is, it's not like something that we used to do. This is used a lot now. In the current things, sure, it's the computer packages doing it, but there's a lot of talk of quartiles. So, that's what quartiles are for. Now, here, this probably looks very odd, but all I've done here is just to get what sort of things do we do when we're splitting data into quartiles. And these are all different questions. Like, let's just look above the line for the moment. If we were asked to split that into quarters, it may not work out pretty. But the first thing I'll do to put data into quarters is find the halfway mark. Same as last week, find the median. What's the median of this data? I'd have 3 numbers here. 3 is the median of this data, okay? Which here I can also call Q2. Now if I'm looking at the halfway mark on either side, so I've already split into half, now half the halves, it's like I put my finger over the 3 and just say what's the half of these? And I'm going to say it's 2. It's like if I put my finger over the 3 and I'm just looking to the right of it. There's my Q1, Q2 and Q3 for this data. Okay? So after I put the middle number was circled, I ignored that. Looked to its left and looked to its right. Okay? But look what happens in the next one. It's not one central number this time. The central number, the Q2, is actually 3.5. Same as last week. What's the median of this data? If you get 2 numbers in the middle, go halfway between them. So the Q2 result here is 3.5. And when I want to split both halves into half, just do it, just look to the left of the line and the right of the line. To the left of the line, I've got 2 in the middle again. Well, the average of 2 and 2 is Q. My Q1 is 2. My Q3 is 4.5. Okay, hopefully it's logical. Then look at the next one. So far we've done an odd set of numbers and an even set of numbers, we're back to odd. What's in the middle here? It's the number 4. Okay, that's my Q2. When it's like put a thumb over my 4, I go, well, what's in the middle here? 2. What's in the middle here? 5. Q1, Q2, Q3. The next one, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'll put a line in between. My middle data is halfway between 4 and 4. The middle of the data to the left of the line is there. The middle of the data to the right is there. Okay, see the pattern? Central number here, cover that over. The middle to the left is that. Middle to the right is that. I've split into 4 bits again. And my last one here, I've got 2 central numbers, so I'll stick with what I've been doing, which is, come on, erase. You meant to erase now. Nah. What about there? Thank you. What about, okay. So my middle is 4.5. I've got a Q1 here of 2.5 and a Q3 here, halfway between 6 and 8, 7. So that was just multiple examples of how do we do it manually. When we've got a big set of data, okay, it's different. We'll just use the ogive. Okay. So from an ogive, if I want to do the quartiles, well, it's pretty nice actually. First we look at how many scores we've got. Because the halfway mark, we're going to go to it. The number of scores here, the trap here would be to go to 90 and say, well, it goes up to 90, but it doesn't really, does it? It stops here. There's 80 scores. So if I want to split 80 scores into 4 equal bits, 80 divided by 4, that's 20 per bit. So all I really want to look at is splitting this data, which went all the way up to here, into 20s. 20, 40, 60, 80. That's going to be my splits. All of them there. But the actual values of this will be my Q1, Q2, Q3. The actual values of it isn't 20, it's just a 20th score. What is the 20th score? Take it across, hit the ogive, and bring down. So the first quartile, second, third, take the first quartile across, hit the ogive, come down, and we're going to do a bit of an estimation here. If that's 3, that's 4, that's 3.5, maybe about 3.8. Okay, some people might get slightly different answers, that's okay. What about this one? We take this across and hit there. That looks like about 4.4, because that would be 4.5 there. And the third quartile here, take it across till it hits the ogive, looks about 6.1-ish. So that was us finding the quartiles from an ogive. The data started about 3-ish, went to about 7-ish, maybe up to 7.5, we can't tell from this. But the quartiles are about 3.8, 4.4 and 6.1, splitting the data into 4 equal bits. We'll do an example of that coming up soon. We've got a few. But while we're at it, interquartile range is something that we talk about in stats, and it's just Q3 minus Q1. Again, yes, resource sheet, absolutely. But it's Q3 minus Q1, meaning here's the data we did before, where we had Q3 here and Q1 here. We said that Q3 was, I'll come back to that, Q3 was 8.5, and Q1 was 3.5, so my interquartile range is 5. It doesn't mean that much to us maybe with made up data like this, but the interquartile range is saying what's the range of the middle data. So if I had all of this middle data, what's the range of it? It only ranges by 5. 8.5 minus 3.5 is 5, that's the interquartile range. And it's not affected by unusually high observations. This number could be 9,864. It doesn't affect the interquartile range. It affects the whole range. If that stupid big number was there, it would be 9864 minus 1. The range would be 9863. But the interquartile range is not affected by freakishly large or small numbers. So it's a reason why it might be used. As long as we know it's Q3 minus Q1. So let's do an example here. We're just going to go through a few of the things we just did. Here's an ogive of the weights in a herd of cows. Okay. How many cows are there in the herd? Yep, we can line this 60 here. Absolutely. 60, because it did go up. It's a cumulative frequency. It went up to 60. What's the median weight of the cows? So we can see that the median for data of 60, someone playing something? So, we can see 30 kilos is not the answer. Well, one would think not. But I just want to know the median cow, if I line all these cows up from slimmest to least slimmest, I'd want to walk to the 30th cow and weigh it. Okay? What's the 30th cow weigh? Bring it across, bring it down, that. Okay? That's the median weight, which looks about 137 kilos. Okay, so median. I could also have asked for the Q2, it's the same answer. Okay? Below what weight do 25% of the cows lie? 25%, that's a quartile. That's saying what we did before. What if I split these cows up into 4 equal groups? I'm going to have, well, I could say my first group was, in the previous question, the median, the Q2 took me there. I don't need that here. But if I want to split this half, I'll go to the 15. I'd go to the 15th cow. Between 0 and 30, the 15th cow, I'm sure I've got a prettier one here, goes to there, which is 128 kilos. Okay, so that's the point at which the first quarter of cows go up to 128 kilos. Hence, below what weight do 25% of the cows lie? 128 kilos or less. I assume I've got a 75% question. Oh, what's the upper quartile of this data? It's exactly the same question as saying, what is Q3? It's exactly the same question as saying, above what weight is the top quarter of the cattle? These are all questions that are about splitting it into one bit there, another bit there, another bit there. I'm just splitting these things into 4 bits. And this time, when I bring that over and down, 147 kilos. So we've just found Q2, Q1 and then Q3, just by splitting them into 4 equal sections in order. What's the interquartile range of this data? Well, we've already done the numbers. We found the Q3, well there was the Q1, which was 128 kilos, and the Q3 we just did in the last one, which was 147 kilos. So it's 147 minus 128, Q3 minus Q1, interquartile range. In other words, the middle half of the cows range only 19 kilos in mass. Overall, there might have been a much bigger range, but the middle half were 19 kilos. So estimate the first quartile of the following data. Again, first quartile just means Q1. It means I would look to see how much data I've got, and I don't have 50, it stops at 40. So I can then consider if I split 40 up into 2 bits, I'd have a halfway mark at 20. I'd split the upper bit there and the lower bit there, but which one of these is the only one I care about? This. My Q1, Q2, Q3 aren't asked about. The first quartile is right here. So if I take that across and hit there, there's my answer right there, 20. The first quartile of this data is, the first quarter is up to the 10th. 10th hits the ogive, comes down, 20. Okay, so hopefully you see that's why we're making an ogive. Whether there's a histogram behind it or not, it doesn't matter, we use the ogive. Now, what is the meaning of that? The first quartile of the data in the question just then was 20. What does it mean? Does it mean 20 results were low, 1/4 of the results were less than or equal to 20, 20% of the results were less than 25, or none of them? Does any of them make sense, what it could mean? Remember, these quartiles are all just about splitting the data. Here's small cow to big cow. What does this do? Well, there's cow, cow, cow. All this stuff does is, I'm sorry mate, is split them into 4 equal bits. And B is all it's saying. If the first quartile of the data was 20, it was just saying that 1/4 of the cows were 20 or less. If the third quartile was 80, it was saying the top 25% are 80 kilos or more. So that's all it's saying. 1/4 of the results were less than or equal to 20. Okay, a 5-number summary is something that we can say about, again, we could have a whole stack of data, and a 5-number summary might be enough to give us an idea of what happened in it. And all a 5-number summary is, what's the minimum of the data, what's the maximum of the data, and what's Q1, Q2, Q3. So that actually tells me a lot. If someone were to say, look, I took 200,000 results, and this is the 5-number summary, that's enough to tell me heaps. Okay? So, let's find a 5-number summary of the following data. Number of cigarettes smoked per day by 10 smokers that were interviewed. Well, the first thing I'll do is, I know that my 5-number summary is my min, Q1, Q2, Q3, and max. Min and max are easy enough to find out, but to find the others, I know I want it in order. So, let's get it, what's the smallest? 5, 5, 10, 20, 20, and another 20. Have I missed anything? 25, 25, 25, 35. Okay. All right, max and min are pretty obvious. The min is 5, and the max is 35. All right, 2-number summary done. Where's my middle point? It's going to be my Q2 spot. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5 on either side, that's my middle spot. What's the average of 20 and 20? 20. So my Q2 is a 20. And then if I halve either side of that line, I've got a halfway mark there and a halfway mark there. Perfect. My 5-number summary is 5, 10, 20, 25, 35. That's it. Min, max, Q1, Q2, Q3. We could find that from an ogive as well. Just be asked, what's the 5-number summary? Normally when asked this, people make stuff up and say the 5-number summary is the standard deviation and the range, and then go on with something else. It's just not. Min, Q1, Q2, Q3, max. Okay? That's my 5-number summary. So what's a 5-number summary from the cows example? We'd already worked out most of it. And I didn't do it pretty on it. Oh, that's annoying. Okay. It was 60 cows. We went to the 30 mark. We took it across here and went down and called this 137. The 15 mark we took across and we hit here and we took that down and called that 128. So we had the 15 mark, the 30 mark, the 45 and the 60. The 45 came across here and hit here and came down here, and we called that 147. So that's Q1, Q2, Q3. Apart from all that, all I need is the min and the max. The minimum result was down here at 110, and the maximum result was up here at 170. There is the 5-number summary: 110, 128, 137, 147, 170. Sweet. Now I know it seems you're bombarded with new info, but all these box plots are, and again, they're a big thing in stats, is just a picture of that 5-number summary. Okay, and it's to scale. Okay, it can still be a sketch, but here's a box plot, and that can be horizontal or vertical. But this box plot says I've got a minimum of 1, I've got a Q1 of 3, a Q2 of say 4.5, a Q3 of 7, and a max of 9. And just visually, I can look at that and say, well, half of my data was in between here. You'll also hear them called box and whisker plots. It's like this is the box bit, or there's 2 boxes and there's a whisker on either side. But that's just how we draw them. How high should it be? It doesn't matter, you know, just roughly that. There's no vertical scale on this thing saying you must draw it so high. As long as you're showing the guts of the data in the boxes and the little whiskers that go to the min and the max. And the very middle line is probably of most interest, well, depending on what you're analysing, that's the median. The very middle cow's weight, whatever, is right there. So let's look at this. Last week we introduced negatively or left-skewed distribution, symmetrical and right-skewed. You can see that just in a box plot. Again, here's the tail. All the data hung around here, but there's a bit of a tail. The tail's to the left, hence we call it negatively or left-skewed. This tail is to the right, hence it's right-skewed, and this is nice and symmetrical. So a box plot can do as much for you as your frequency distribution. It's not as accurate, but yeah. Last week I was doing some analysis on our numbers. On the left up the top there, that's question 1 to question 6 from our mid-semester. And on top right is quizzes A1 to A6 from this year. And you'll see that the box plots side to side, when we look at the questions in the mid-semester, and these are the topics for Q1 and A1. Well, clearly we liked Q1. Notice this program put 2 outliers because the results were so together up there that those 2 results were considered out of the norm. We don't go into outliers anymore, but anyway, they're just a way to describe ones that were a bit unusual. Clearly, quiz 2, or question 2, I should say in this one, here's a bit harder. Our results range from 0 to 12 out of 12. As they did for questions 4, 5 and 6, we got the full range of results, 0s through to 12s. So you can see that everything was very spread. And if you just want to look at what were the middle mark, well, I can see a bit of a graph here. And I can just look at them and say, clearly question 1 was our favourite, and question 4, linear functions 2, probably because it followed on from the first week, we also did well. In terms of the quizzes when we first hit them, we can see similar, not the same, but fairly similar sort of pattern where, for whatever reason, linear functions was liked more than the others around it. So anyway, they're box plots, that's why we use them, and what they're for. So here's use a box plot to represent the data from the smoking example. Well, there they are in order. We'd already worked out from the smoking example that we had a Q2 of 20, we had a Q1 of 10, we had a Q3 of 25, we had a minimum result of 5 and a maximum result of 35. So if all I'm doing is turning that into a box plot, I just know that my main box area is going from 10 to 20 to 25, from 10 to 20 to 25. I didn't make those heights anything in particular, I just made it look roughly like that. But there we go, 10 to 20 to 25, and my whiskers went down to a 5 and up to a 35. Oops. Yeah, box plot done. That's my visual representation of the distribution of results. And if someone asked me the interquartile range off that, I could work out Q3 and Q1 from that and do a subtraction. I would say, well, it's 25 minus 10. If I was asked, it's probably coming up for all I remember, is equal to 25 minus 10, the interquartile range would be 15. Okay, so we can get all sorts from it. As long as you just remember min, Q1, Q2, Q3, max. And we're gold. Okay, ask us another question. That's what I was thinking. Okay, find the interquartile range of the following data. Again, as long as we remember, all I care about is my Q1 and Q3 and doing a subtraction. My Q3s are 7, my Q1s are 2, so 7 minus 2, yep, my interquartile range there is 5. The middle half of data has a range of only 5. The range overall is 9, 10 minus 1, but my centre of data has a range of only 5. Okay, this one just wraps it up. It's already written out in the book, so I won't go particularly slow with this, but it's deaths from measles and deaths from cancer. Some pretty olden day data. Deaths in London from measles and cancer. Actual data, 1647 to 1660. So first thing, I would place them all in order, okay? Because I want to work out Q1, Q2, Q3. Determine the 5-number summary for the sets of data. Okay, well the middle is right there, which leaves me with halfway between 27 and 33 is 30. I've got a halfway mark on the left of 8 and on the right of 74. I've got a min of 3, a max of 153. So there's my 5-number summary. On the other set of data, I just do exactly the same stuff. Split into halve the halves. So there's my 5-number summaries. Again, that's not visually anything too helpful. But if we now draw a box plot for each, and look at the deaths from measles, do a 3, 8, 30, 74, 153. Initially it's already showing very right skewed. There's a tail of data to the right. The majority of stuff is down here, but there was definitely a right skew going on there. If I look at the cancer from 19, 24, 30 and a half, 37 and 63, well, definitely the deaths from measles had a much bigger range, much bigger interquartile range, much less tail, but they were still both right skewed. Okay, both were still definitely had a tail heading off to the right. But overall, their median was the same. Okay, look at that central line. The median result for both looks pretty much exactly, well, 30 versus 30 and a half. Okay, but we can get a lot more data from that. So if we compared the measles to cancer, we can see the similar medians. Much larger range from measles, absolutely. Both right skewed. Okay. Now, last week we mentioned it, but didn't get into it, that there are 2 different types of standard deviation, or types of data first. Population data and sample data. We said population is when we had all the data. Sample was when we only had a bit. Like if I did an analysis of everyone's opinion here on politics, I would have a sample of Newstead. So if I wanted to say Newstead people think this way, I only had a sample. But if all I was interested in what this classroom of people think, then I've got population. If my results aren't going to try and imply Newstead people think this way and just say the people in this room right now today think this way, population data. Okay. Now, last week's lecture, as he said, we only looked at the standard deviation of population data, and that's not going to change. That manual standard deviation we did last week, we're still going to do exactly that way. This week we're going to say, look, you got that. Just how do I get this out of the calculator? The manual questions will still happen. Like last week's question, you do this manually, just to get understanding. They're still going to ask, fill in this table, work it out manually. But if it doesn't ask, calculator's fine. We want to work out how to do it on the calculator. And there are these 2 different types of standard deviation. Notice I let one slip through into the worksheet. I had this on the worksheet last week. I didn't mean to, since I hadn't introduced it yet. But all we've got here, this formula we looked at last week, the difference is last week we said standard deviation equals, this was just the sum of that column at the far right, n was just the number of scores, and we said, well, that's the average squared distance, and we square rooted it. So the formula looked horrid, but when you had that table there, it's like, fine. And we don't need the formula this week. We're just going to shove it in the calculator. But the only thing we're introducing here is standard deviation on your calculator will look like this little symbol, and it's a sigma. Okay, it's one of the Greek letters again. Unfortunately, that is a sigma, and that's a sigma. They're both called sigma. One's an uppercase sigma. The one we called sum, that's an uppercase sigma, and that's a lowercase sigma. You see they're both related to standard deviation, but the lowercase sigma, whether it either says sigma or sigma n, depending on what calculator you've got, just means population standard deviation. The one you do when you've got all your data. The standard one we did last week. The other one that's sample standard deviation, there's two ways your calculator may express it as. It might just use S for sample, which is nice and easy, or it may have a sigma with a subscript instead of n, a sigma with a subscript of n minus 1. And the reason that is because the formula is almost exactly the same formula. But look, this one had an n, this one had an n minus 1. Again, don't write these formulas down. You don't need them. The calculator's got them in it. But why is the sample one called n minus 1? Because the formula, the only difference in the sample formula is a little n minus 1. So why use n minus 1 instead of n? If you imagine if I decrease the denominator by a tiny bit, I actually increase the size of the number. Like if I've got 100 on 4 versus 100 on 5. Think of 100 on 5 equals 20. If I decrease that denominator, 100 on 4, I actually increase the size of the number. I think it's what you could call a fudge factor. Imagine if I was asking you a question about your political views and saying that you represent New Step. Chances are if I had everyone from New Step in there, I'd get a few more extremes. So the assumption is that if you're doing a standard deviation on only a sample, the real mob of everyone would be a little bit bigger. What does that n minus 1 do? It makes that a little bit bigger. Not very scientific. A lot of maths people, historically including myself, don't like stats because it's very, yeah, this will do. Yeah, it's close. That's pretty good. And that's not very mathy. Okay, but that is what it's for. Now, how far do we need to go with that? Not. As long as you know which one to get out of your calculator, which button to press, fantastic. As long as you understand that the population one is always going to be a little bit smaller than the sample, because the sample population, the sample standard deviation, it's used that n minus 1. It's made a little bit higher. As long as we can use our calculator and find out, we're good. And let's do that. Just check the calculator for a sec. And now, actually first, I've lost most of my calculators. Anyone got a FX82AU nearby? Like the standard? Thanks. So on the one that most of us have, what? No, yeah, it's good visuals, isn't it? Yeah, that's perfect. So now it's clear for everyone. Oh, okay, that's still not very much focus here. It's a horrible visualizer. Anyway, we'll make do with what we've got. Light off any better? Yeah, that's much better. Okay, if I want to go into stat mode here, it's still, when we did regressions of that, we still had to go into stat mode, it's still number 2. The difference here is instead of A plus BX, which was regression mode for week X, it's single variable. It's just option number 1, which means I'm just going to put in one variable. I'm going to put in some numbers. Okay, so it's option 1 this week. Some of you might have an F column next to it already, or it doesn't matter whether it's there or not. We're not using it. So if you've got an F column, it'll just fill with 1s, ignore it. Say I want to find the standard deviation of, what was the one in the book? 2, 4, 6, 7. On this calculator, I'll go 2 equals 4 equals 6 equals 7 equals. Just like before, the equals is like the enter key. And then just like before, I've also got to press all clear, because otherwise any answers I get, it'll chuck it back into the thing. So stick your data in, press all clear. Now I'm still back on the 1 key. It's in yellow writing, so shift 1 gives me all these options. And variance. This topic is variance. And then you can see the little n will tell me how many numbers I stuck in, which should tell me I put 4 numbers in. You bet I did. If I go back into variance, Option 2, the X with a hat on it, that's X bar. That'll just tell me the average of 2, 4, 6, 7, which you may want to use in your other questions. And I go 2 equals the average of those numbers of 4.75. Cool. The first one versus the second one, it's got a sigma and an X, and that's got an S and an X. Sigma is the population, S is for sample. So for this calculator, as long as we know that difference and we read the question, what's the population standard deviation of those numbers? Well, it'll be option 3. It'll be 1.9. On average, 1.92. Those scores are about 1.92 away from the mean. If I go into the same thing and go for the sample standard deviation, it's a little bit bigger. Instead of 1.92, it's 2.21 or 2.22. Okay? Now, just say a lot of us have this type or the sharps in general that look something more like this. If you don't have the table come up, like if I go mode, I'd go standard deviation. And then as I put all the data in, I've got to press M plus in this model. So I did 2, 4, 6, 7, I go 2, M plus, 4, M plus, 6, M plus. And after each time it tells me how much data I've got. N equals 4 bits of data. And then on this one, some of them you're going to have, like on the sharp, the EL531s, you'll see standard deviation under the keys, 5 and 6 I think. You'll see your standard deviation ones there, your S or your sigma. On this one, it's down in S var, and there they are. On this calculator, option 2 is the population, option 3 with a little n minus 1 is the sample. Okay, so I know that's very rapid. Check, mode. Oh, now all of them, to dump your memory, just go back to mode 1 and it gets rid of any data you put in. So that's the calculator entry. We don't spend much time on that because you just get to know your own calc. And if in a question exam gives you a table and says fill this in to do it manually, great. But the question also might just say, just what is the standard deviation of these 4 numbers? You could either look at the multiple choice and go, well, it's not you, or just know how your calculator spits it out. We'll put the 10-minute break in there.
I missed the first compliment. Is the histogram just about getting rid of all that
Just so you can do the other.
So it's just a plot. So there isn't going to be much about the histogram part. But it's all about the archive data, nothing about the
Exactly. You do the histogram just so we're doing the archive, and then we're only using it.
Awesome.
Cool. You have fun? Yes. Good. Excellent. Hey.
I can't remember dropping after this. I might have to give these to you.
Yep.
But wait, I want to check one. No, wait, this one. It says A and B represent each other. And I've written down that it's the white, but is that
True,
wrong, or-
but in real life on it, like as in, what were we plotting there? We were plotting, we had years, 1, 2, 3, 4, 5, time and height. So the height was about 0.8 metres, and then about that.
Yeah.
Looking at that, A represents the y-intercept, true. What's the real life interpretation? A is 0.37. What does that mean in that picture, do you reckon? Didn't the heights became 0.8 and 1.2?
Is that what? No, where it started. Yeah.
Because we didn't even measure at t equals 0, did we?
No.
But that's what sure, I mean I haven't drawn this to scale, that's 0.8 already. I should have drawn it steeper. But what was that? Initial height.
Okay.
And what about B? Given that B is rise over run, B is the gradient,
Yeah.
what do you reckon that's saying? Yes, per what? It's exactly what it is. Okay, because it's height over years, and it's saying every year how much it went up, every year how much it went up. So it started at 0.37 metres and went up per year about 0.41 metres.
Okay, so that's what.
That's exactly.
Dave, you can read on your pen, mate. Okay, cool. I just wanted to double check that.
Sweet.
There's those ones.
Good.
Thanks.
Okay, carrying on with this, we've covered two types of standard deviation, only care about it from the calculator, some cumulative frequency graphing, and some ogives and quartiles. Now this normal distribution, this is one of the main, or a very large concept in stats. So, if you look at that frequency histogram there, we already know frequency histograms are boxed, it's not cumulative frequency, and we could draw something like that on it and say, look, most of the things happen in the middle, it's a symmetrical distribution. We call that a normal curve. And a lot of things in life are going to, if we sketch them, it would come out like that. I've got an example coming up. Here's one, okay, survey of 50 female student heights, centimetres in this maths, and a survey of 50 male student heights. Okay, I faked it, but just pretend that happened. I think it would be moderately realistic. We can see a trend there. It's a fairly normalish sort of curve, average height, no huge tail, it's not skewed. Fairly normalish sort of curve for the men as well. The only difference is there may be a step higher, okay, biologically. So we describe a situation where the values are most common near the mean. Well, that makes sense. Values are just as likely to be below the mean as above the mean because the whole thing's symmetrical. And extreme values occur rarely. Again, that's a normal distribution. That happens. You'll get exceptionally tall, exceptionally short, but it's rare. Most of the results are all in the middle under this curve. Here's an example of what we're leading up to, because we're going to make some outlandish sort of statements soon that say, look, if I measured everyone's height at uni, say all of the males, that I reckon I'd get some curve like that. And then I'd make a statement that I bet you 68% of all of the males' heights are within one standard deviation above and one standard deviation below the mean. And 68% seems to come from nowhere, okay? So we're leading towards that. But firstly, this scenario, imagine planting some grass seeds and then measuring the length of every blade after a month. Would you expect them all to be exactly the same length? Well, they'll probably all be an average rough height, but there's probably a little bit of variance, a bit of random variation. There might be a freakishly long hair, blade of grass. There might be a really short one that was quite stunted. Okay, not hairs. And here's one prepared earlier. Say we measured, and this there was a 5 centimetre of grass and a 6 centimetre bit, a 3, there was another 5. I was just rounding them off to the nearest centimetre, a 4, a 5, and then so on. I just kept measuring bits of grass. This sort of thing can potentially happen. That clearly the average bit of grass, the mean grass, is about 5, 6 centimetres. But occasionally there'll be a stunted one that maybe was under the surface, whatever. Random variation will come in. And it's going to form a normal curve. Okay? We can take that to the end. That will happen. Unless I've got something else going on, unless half of it's got sunlight, half's got shade, only water half, unless I do something deliberate, random variation is always going to end up looking like that. For a normal distribution, this is where the statements seem a bit, where are you getting that from? 68% of the data will lie within one standard deviation of the mean. So say the mean of the bits of grass, say we measured all the bits of grass and the mean height was say 6 centimetres, and let's say the standard deviation was 1 centimetre. Not on average, they're all, one higher, one lower, with some extremes, then what I'd say here is the mean is 6. Standard deviation, down 1 standard deviation from the mean is 5, up 1 standard deviation is 7. And what I'm claiming is 68% of all those bits of grass will lie there. And again, where does 68 come from? Well, there's a formula, but life doesn't have to follow a formula. Life will do whatever it does, but the formula has been derived from life, from real life experience. I've got another example in a sec. So 68% will lie in there, 95% will lie in there, which in this scenario would be 6 plus 2 and minus 2. That's saying 95% of all the bits of grass would have been between 4 and 8 centimetres, and 99.7% would have been between 3 and 9. Hardly anything, 0.3%, 3 out of 1,000 blades of grass would have been freakishly short or long, as in less than 3 centimetres or greater than 9 centimetres. So that's the summary of where we're heading to. 68, 95 and 99.7 are 3 magical values which I'll show you what's a good thing to have on the resource sheet soon. Those numbers are good, but there's another split. But firstly, a quincunx. This is another way to show what we're talking about, that, you know, our real life doesn't have to follow your maths formulas, but this is another way to show, but it will. Imagine this, you get all these little balls there, and they come down and they hit a peg. And every time they hit that top peg, on average, half of them will go left and half of them will go right. And then they might hit another peg. They might go left, they might go right. If you imagine all the probability in there, you can do maths on this and just talk about all these options. And here's one that does it. I've seen one in real life where it's a wooden peg sticking out of the board, but here's the digital one that just goes off. We can probably do it faster. And it just models what would happen. And it's not pre-programmed, it's doing the stats while it does it. It's doing probability. Half the time it's doing this, half the time it's doing that. It doesn't promise you it'll come perfectly symmetrical. And it's not at the moment. We've got 17, 18, 17, 20, and it's not a promise, but it's where you do that 1,000 times, 2,000 times, it's going to happen. It's going to become near perfectly symmetrical. And so that's where we get our 68, 95, 99.7. If it's just random variation, it's got a 50-50 chance of going either way at each obstacle, that will happen. I think, did I put it on here? Ben left one going for days once. I'll leave that going. Did I put it on here? Yeah, that's the one. Ben left that going for days. And can we even read the numbers there? But you can see the 2 in the middle actually end up very even, but you can see that's pretty nice and symmetrical, okay? Not perfect. One ball went out there, none did there, but anyway, point made, they're the perfect percentages that we believe will happen unless something else is going on. Now, as for what I recommend, we'll see soon, well, what are you going to ask us about this? Firstly, I just want to fill in this chart down here. And this is the chart I'm going to recommend. This is resource sheet gold. If you can put this bottom chart on there, I just want to show you where I got it from. Imagine first, 68% goes between here and here. Well, if 68% goes between here and here and it's symmetrical, hopefully it makes sense that half it'll go here and half it'll go here. So that's why I've labelled that 34, 34. That makes my 68. Okay. Then if I'm saying, well, 95% of the data lies between here and here, but I've already counted for 68% of the data in the middle, then if I want to know what should go here and here, well, I should do a subtraction. What's 95 minus 68? And then halve it. It's 27% needs to fit in this bit and this bit. Half of that is 13.5. So that's why 13.5 goes there and 13.5 goes there. You can say, look, I don't need this proof, David. Just give me that. Well, true. Just want you to see where it came from. Then, if 95% fits between here and here, 99.7 fits between here and here, then do that subtraction and divide by 2, and that tells you 2.35% lies in there. And overall, we should have 100% of data under this curve. 100% minus 99.7 is 0.3%. So 0.3% must fit in the tails, halve it, that's 0.15% in each end. So that's the picture I'm saying, that whatever the mean is, it goes up by standard deviations, goes down by standard deviations. We've got a few examples to make sense of it, but they're the magic numbers. If you can write them, and it's symmetrical, so you only really need to write 4 numbers. That covers everything. All of those percents add up to 100. So let's use that. Here's a fairly wordy sort of question, but also very predictable. The mean life of a particular brand of car battery is 4.25 years with a standard deviation of 6 months. So initially, in reading that, it's telling me that it was really normal for cars to have a 4.25 year life, but it was normal to maybe go 6 months longer, half a year longer, or half a year shorter. In fact, 68% of all the batteries will be between 6 months either side of 4.25 years. If the life of a particular brand of car battery is normally distributed, there's a hint to say, look, if it's normally distributed, these percents work. Find the percentage of cars. Well, let's just look at that first. We want to know what percent are greater than 4.25 years, between them and that. First, let's set up a picture. The first thing I'll do here is nick the mean and the standard deviation. And here I've noticed they're different units. So I'm going to think I've got 4.25 years mean and half a year standard deviation. 6 months is a half. So if I set that up, I'm saying I've got a 4.25 mean, and I can go up by half years. From 4.75, 5.25, 5.75, and I go down by half years. 375, 325, 275. So there's my x-axis, just with the mean and standard deviation filled in. All of those percents are going to answer my questions. My first question was, what percent will last greater than 4.25 years? What percent, do you reckon, is to the right of 4.25 years? If it's perfectly symmetrical, half of them. Half above, half below. So percent greater than 4.25 years, definitely 50%. Same question for under 4.25 years. What about between 3.75 and 4.25? Between here and here, it's done for us. 34%. What about between 375 and 525? Well, now it's asking for all of this range. What do you reckon? Add the 3 bits up. The 234s make the 68. Add the 13.5 onto it. 68, 78, 81.5%. So if you've got this thing, you can answer all the questions. We're not going to ask you about what percent to do with 4.3. I don't know the answer to that. It's going to stick on the boundaries. What about another one? More than 5.75 years? Well, only 0.15%. So not many. 0.15% will last longer than 5.75 years. All right, let's check the next questions we had on there. If 2,000 batteries are sold in a month, how many could you expect to last more than 4.75 years? So notice it says now how many. It's not just what percent, but how many. So first we're talking more than 4.75 years. So firstly, I want the percent to the right of that. I could add up those 3 bits, or I could just think, look, everything to the right of halfway is 50%. Take 34 off it, it must add up to 16. The 34 and the 16 must make that 50. Either way, it's 16. 13.5 plus 2.35 plus 0.15%, 16%. So if 16% of all batteries, I would expect that to happen. I just need to work out what is 2,000 times 16%. Okay, so I'll just lose some zeros, and it's going to be 320. That's how many batteries I would expect to last this long. This is the sort of stats that battery manufacturers have got to do. Their batteries will do whatever they do. They'll get a mean and standard deviation. What sort of guarantees should they put in it? Should they promise, if the mean battery life goes to 4.25 years, should they promise it'll last 4.25 years? No, because there's going to be ones that go under. But anyway, that's all part of marketing and not us. But here's the question I was talking about. If the manufacturer guarantees to replace any battery which does not last 3.25 years, in other words, does not last this long, is saying that long or less. So he already knows that no matter what he does to his factory, he's going to produce batteries that fall short. And he's got to cost that into the price of the battery. So what percent will fall short to the left of here? 2.35 and 0.15. That's 2.5%. That's how many will fall to the left. And what percentage? Okay, he didn't ask how many, just what percentage. 2.5% of all the batteries he's made, he may have to give money back or replace. Okay. I think that's it for the questions on that. Okay, another very predictable question. And in the question, it's just going to give me, I need a mean and I need a standard deviation. I don't care whether it's sample or population, depends on the question. I'm going to do exactly the same thing. And here, the key parts of the intro here, oh, that's a typo of mine. You should write elephants on it for me. I should state the units of the standard deviation too. So I've got a mean of 2.9 kilograms. What is it? Babies. Okay. So initially what I want to do is I want to do a picture. I want to say, look, I know this. It's on my resource sheet. I know my mean goes in the middle at 2.9 kilograms. And I know that I've got 3 standard deviations going this way and 3 standard deviations going this way. And I know I'm going by 0.3, so 2.9 becomes a 3.2, becomes a 3.5, and a 3.8. And going down by 0.3s, I've got to have a 2.6, a 2.3, and a 2.0. So they're the kilos I better be getting asked about. And I know the percents from before, or on my resource sheet, it's 34%, 13.5%, 2.35%, and a 0.15% totally symmetrical. 34%, 13.5%, 2.35%, and a 0.15%. And then I say determine the percentage of infants who weighed between 2.6 and 3.2, between there and there. That was the good old 68. That's up and down, plus or minus 1 standard deviation from the mean. I'll expect 68% if it's normally distributed. Between 2.9 and 3.5, well, between 2.9 and 3.5, that's just these two added up. A 34 and a 13.5, so a 47.5%. Under 3.5 kilograms, well, that's the vast majority will probably fall under 3.5. So remember, yes, I can add all of them up. Or the quicker way is, if you know that everything under there is 100%, we know that, you could just take these, sum these, and take them off 100. Okay, it's the same thing as adding up all of them. They add up to 2.5%. All the others are going to add up to 97.5%, because that's 100 minus the 2.5%. Between 2.3 and 3.2, 2.3, 3.2. It's between there and there. We did one of them on the previous page. 81.5% that ended up being. And under 2.6, well, that's from here and under. Under, it's that plus that plus that. 13.5 plus 2.5, well, it's 16 again. We already had one similar to that. Okay, that's how our percents come. If you got your mean, you got your standard deviation, and hopefully that grass thing made sense as how could you possibly predict this? Yeah, that's what happens. Okay, that's the pretty version. Fine. We did it. Now, this is leading on to the last concept we've got to deal with. Pretty sure. Z-scores relate to normal curves. Shelby sat for 2 exams. The mean and standard deviation along with Shelby's mark on each exam are listed below. Assume the marks on each exam are normally distributed, like the class's marks. Yeah, still came out like that. In which exam did she do better with respect to the other students? Now, it could seem like a weird question because, well, the class got 72 on average in chemistry. The class got 72 on average in maths. Shelby got 78 in chemistry. Shelby got 78 in maths. So on the surface it seems like, well, she did fantastic, equally fantastic on both. She got 6 marks above the mean in both classes. Identical performance. But if you look at the standard deviation of the classes, what did she really achieve here? She scored 1 standard deviation above the mean. It's impressive. But 68% of all people were going to be within that 1 standard deviation of the mean. What did she achieve here? The marks were much tighter. The standard deviation was only 3, meaning 68% of the results were between 69 and 75. She got 78. That's massive. She's down to one of only 5% that were out in this extreme range. So that's the concept here. If we look at the picture, it explains it better than me. Chemistry. There's the curve, and if we fill everything in, chemistry had a mean of 72, and the standard deviations went up by 6, and Shelby, got 1 standard deviation above the mean. Brilliant. If we do the same thing for maths, 72 would go up by 3 to 75. That's what she scored. So that's just saying again, the more standard deviations above the mean you've gotten, just the better you've performed. You've done exceptionally well. So we can use standard deviation and mean to compare performance in certain classes. And then again, that's the comparison. She was in the top 16% of that class. She was in the top 2.5% of that class when you look at the one-sided distributions. That was just a lead up to this, okay? And this is talking about z-scores, which converts any normal curve into a standard normal curve. Now, a standard normal curve, just think a standard normal... Did I draw a picture here? Great. A standard normal curve is exactly what we talked about, but with a mean of 0 and a standard deviation of 1. So a 0 in the middle going up 1, 2, 3, and down -1, -2, -3. So if I said, look, I'm Shelby, I got a z-score of 0, I'm saying I scored equal to the average for the whole class. A z-score of 0 relates to being dead in the middle. If I said I got a z-score of 1, what I'm saying is I got 1 standard deviation above the mean. If I got a z-score of -2, I'm saying I got 2 standard deviations below the mean. So a z-score is a way of describing or comparing. If I said I got a z-score of -2, Gilbert got a z-score of -1, he did better than me. We both got below the average, but I got 2 leaps of the standard deviation below the average. He got 1 leap of the standard deviation below the average. It is better being more to the right. Now there's a formula. It's worth noting, yes, the formula may be needed, but some of you will use the formula and some of you will this might just make pure sense when we get into some examples. Let's check. And this, I think, is a really good example to get a concept of what's happening. So in an English exam, the mean mark was 60, rightio, mean equals 60, and the standard deviation was 8. That's my best sigma I can draw. So, if someone got 68 in this exam, can anyone see what their z-score would be described as? They got 1, a z-score of 1, because their score is 1 standard deviation above the mean. Let's use the formula for a sec. Z equals x minus x bar on SD. That's the formula from the previous page. The x is just the score we're discussing, 68. The mean of this exam of everyone was 60, and the standard deviation was 8. 68 minus 60 is 8, 8 on 8. Yep, there's the formula doing for us. Both ways is good. The formula spits out the result. Nice, I've got a z-score of 1. What does it mean? A positive 1 standard deviation above the mean. A positive 1 jump of 8 above the mean. I got 68. What if I got 52? Hopefully you can see logically if you compare the 52 to the 60 I got below the mean by the same distance. That must be a z-score of -1. Z equals a score of 52 minus a mean of 60 on a standard deviation of 8. Well, that's minus 8 on 8, which is -1. Again, that just says if the mean was 60, a z-score of -1 means I got a standard deviation below that. One of those 8s below is 52. What if the class got 60 and I got 60? What's my z-score? 0. I got slap bang, I got nothing away from the mean. My z-score is my score minus the mean score on 8, 0 on 8, it's 0. Yep, slap bang on the median, your z-score is 0. So 0 is not a bad thing. Is there a question? No? Okay. What about 84? Again, the formula will do this every time, but if I want to think how many standard deviations above the mean, well, that's 24 marks above the mean. That's huge. How many 8s are in 24? 3. It's 3 standard deviations above the mean. This is going to be a z-score of 3. Because the score of 84 minus the 60 divided by the standard deviation is a 24 and 8. In other words, it's 3. Yep. 84 is 3 8s above the mean. 64, well, this is going to be fractional. It's still above the mean. 60 was a z-score of 0. 68 was a z-score of 1. 64 will be halfway in the middle. It will be a z-score of a half, because I scored half a standard deviation above the mean. Half of 8 above it. Formula do it. 64 minus the 60 divided by 8, it's 4 on 8, which is a half. Whether you write it as a decimal or a fraction doesn't matter, it's a half. And the last one, 58, well, it's going to be fractional again. My z-score will be the score I'm discussing minus the mean on standard deviation. If I got 58 and the mean was 60, I've got a negative z-score, but not by much. It's pretty damn good. 58 minus 60 is minus 2 on 8. That's minus a quarter, or minus 0.25. So that's still very good. A little bit below the mean, but still massive. Yeah, well done. Okay, so there's the z-score formula. In that direction anyway. Now, what about in this sense? And it's still the same concept. In another exam, the mean was 64 and the standard deviation was 10. In other words, the majority got between 54 and 74, with 64 being the middle. The lowest and highest z-scores are minus 2.5 that someone got and 3.5 that someone got. What were the actual highest and lowest marks? I'll use the formula in a sec, but I'd rather not use the formula. Because minus 2.5 means I got below the mean by 2.5 standard deviations. What's 2.5 tens? 25. 2.5 times 10 is 25. That to me is instantly saying I got 25 below the mean. Okay, because 2.5 standard deviations below the mean is 64 minus 25, which goes 54, 44, take off the 5, 39. A z-score of 3.5 says I did hugely well. I got 3.5 standard deviations above the mean. Instead of getting the mean of 64, I got 3.5 times 10. I got 35 marks above. Okay? If that makes sense, fantastic. If not, the formula will do the same thing for us. Z equals x minus x bar on SD. The Z is minus 2.5 on this side. The x is the score I'm discussing. I'm trying to work out what score would have got that happening. The mean we know is 64, and the standard deviation is 10. So that's subbing in. It needs algebra. Times both sides by 10 becomes minus 25 equals x minus 64. I want the x by itself. Let's add a 64 to both sides. That's what we did. Same as the other side. I could have used the formula. Z equals x minus x bar on standard deviation. The z-score on the right side is a 3.5. The x is, I don't know, minus 64 on 10, and just undo that one. Again, times both sides by 10. That becomes a 35 equals x minus 64. Add 64 to both sides, becomes a 64 plus 35 equaling an x, and that's what we did. So I hope that it sort of stands out that a 3.5 z-score, massive. Very low percent of people getting up that high. A standard deviation of 3 away from the mean is huge. Okay. So, what statement is true? Billy got a z-score of 0.5 in quiz A6. That's not our Billy, that's a different Billy. I know how to spell Billy, Prince. You're here somewhere probably. I didn't misspell your name. Are any of the following statements correct? Billy got 50% in his exam. Doesn't say that at all. I had no idea what anyone got in terms of percentages. A z-score of a half doesn't tell me he got 50%. Billy got half a mark above the average. I don't know anything about it. Billy got an above average mark. Is that true? Yeah, he got a Z-score of a half. That means he got a bit of above the average. And got half a standard deviation above the mean mark. Well, that's true. Yeah, that's totally true. I can say yes to these, but all it's telling me is I don't know what the mean mark was, but it was there. He got a Z-score not of +1 standard deviation. He got a Z-score here. Yeah, he got half a standard deviation of the mean. Good on him. He got above average mark. Absolutely. What about this one? Amy got a Z-score of -1.3 and Billy got a Z-score of 0.2. Who performed better compared to the rest of the students? Is that hiccups? Nice. Gotta love that in a lecture. And she's leaving. That's it. You can keep you and your hiccups. Yep, all right. Who performed better? Billy did. 1.3 seems bigger, but it's -1.3. Okay? All we're doing there is saying, look, here's mean. Billy was down here at -1. Sorry, Amy was. Billy was here at 0.2. Great. He was above average. Okay. Another one out of the book that's already written out. Just explain it. Jack scored 66 in a maths assessment and 60 in a chemistry assessment. The mean and standard deviation of marks for each course are given in the table. So this is Jack's mark, and this is the entire class's details. In which course did Jack perform best relative to his classmates? Nowhere in this question does it say find the Z-scores. But we need to see that's our way of doing it. If we're ever asked in which way did Jack perform better, if we can just find a higher Z-score for one than the other, that answers the question. It just didn't spoon feed us that. So if Jack's mark, well, we just do a Z-score analysis on both. His Z for maths is x minus x bar on standard deviation. He got 66 minus the class got 55 on 10. So we got 11 above the mean. Awesome. Divided by standard deviation. So he got a 1.1. So he did really well in maths. How did he do in chem? Well, his mark was 60 minus 50 mean, so he got 10 marks above the mean, but the standard deviation was only 8, which means the results were tight. He did exceptionally well. 10 on 8 is 1.25. So he did well in both, but he did even better in chemistry, just because a 1.25 Z-score beats a 1.1. And in the picture, there's my 1.1 for maths, there's 1.2 for chemistry. Now, if Jack also scored Z-scores of -1.6 in English and -2.1 in philosophy, in which of these two subjects did he perform better? What would you rather get if you're trying to achieve a -1.6 or a -2.1? A -1.6. Further to the right. Again, just think it's like on the number line, whether you're pitching in the curve or not. But a -1.6 might be here, but a -2.1 is further that way. So yes, we want the more positive. The closer to the right number is our Z-score. Because -1.6 is greater than -2.1. It's a larger number. All right, last one here. Is it the last one, Ian? Yep, cool. So, predictable sort of question. Harry scored 62 in an English test in which the mean was 50. Okay, he's done well. He scored 12 marks above the mean. The standard deviation was 8. He scored 64 in a maths test in which the mean was 60 and the standard deviation was 5. In which subject did he perform best relative to the rest of the class? I'll do the formulas in a sec, but even just looking at it, he scored 62 when the mean was 50. That's 12 marks. How many standard deviations? How many 8s are in 12? 1.5. So I'm just going to state that I can already see a 1.5 Z-score for English. He scored 64 in a maths test in which the mean was 60. So he got 4 above average. Compared to 5, well, 4 divided by 5, that's how many 5s in 4? Less than 1. So already I'm there, yes. So let's do the actual, do it accurately instead of just looking at it. His Z-score in English was his mark minus the mean divided by the standard deviation, which is a 12 on 8, which, yes, is a 1.5. His Z-score in maths was he got a 64 minus the mean of 60 and a standard deviation of 5, so that's a 4/5, 4/5, which is 0.8. So you can see in which subject did he perform better relative to the rest of the class? He outshone in English. He did better in English. Above average in both, but 1.5. Now, the last trap, algebra 1. What mark would he have had to have achieved in maths for his performance to be equivalent to that in English? So we're changing we're not telling you what he got in maths. We're saying, what would he needed to have done in maths? In other words, question mark, in order to have achieved as good a performance as he did in English. So what it's saying is, maths mark equals, I don't know, but I still know the maths mean was 60. I know the maths standard deviation was 5. And I know that I want him to get a z-score of 1.5, so he's performed just as well as he did in English. That all just goes in the formula. Z equals x minus x bar over the standard deviation. Z-score of 1.5 equals I don't know score minus a mean of 60 over a standard deviation of 5. And then multiply both sides by 5. 5 times 1.5, that's 7.5 equals x minus 60. Tiny bit of algebra left to get rid of that minus 60. Let's add 60 to both sides. That becomes x equals 67.5. So he got 64, but if he got 67.5 in maths, he would have got a z-score of 1.5 and had equivalent performances. Done.
Did you watch the two blokes in there? That was, oh, because I thought I was just really hungry. That was good. Yeah, that was a good mini passion. Anyway, it's fun, aren't they?
Yeah, suggest we
Oh. Anyway. Just down the hall, the passing So it's really your call, you can just go. Then the other thing is, if you want to check what it was, I'll have it at the end of today, I'll read up increasement redemptions, but the zero version of it. Yeah. If you just want to do a redemption on it. Yeah. I'll just read out and see what happened in the quiz.
Yeah, just like do a redemption on it, get like 5.
Yeah. Okay, cool.
Thank you.
Yeah.